Once again, hello everyone. This is the last video for the periodic table. In this lecture, we will complete electron affinity and electron negativity topic. Now we will start the electron affinity first. What is electron affinity? There is one more terminology for the electron affinity, that is electron gain enthalpy. Electron gain enthalpy. And this is denoted with the delta H. And here affinity you can understand as a love for electron or attraction for the electron. So the definition for electron affinity is the amount of energy released when an electron is added to valence shell of an isolated gaseous atom. The electron is being added in the valence shell of any element, and that element or that atom is in a gaseous state and isolated also. That energy, released energy, is called the electron affinity. The amount of energy released when an electron is added to valence shell of an isolated gaseous atom. Here this gaseous, isolated gaseous system is the same as the ionization energy, because that atom first, if it is that atom is in a solid state or liquid state, we have to bring that in gaseous state. Then we'll give the energy to take a electron or release a electron, and this delta HEQ will be negative of electron affinity. Electron affinity is always positive because we are giving or adding an electron in the atom, so the whole process will release energy. And reaction you can write it as A in gaseous, taking one electron and giving energy. Since the energy is released, so this reaction is exothermic. Since energy is released, so reaction is exothermic. And so delta HEQ will be negative and electron affinity will be positive. And successive electron affinity, when we are talking about the successive electron affinity, that means first, this will be the first, A gaseous taking one electron and A minus is being, then A minus gaseous is taking one more electron and A minus 2 is being produced. So this is the first electron affinity, the energy released in this reaction, that is the first electron affinity, that is second electron affinity. and this for every reaction HEQ will be negative and electron affinity will be positive, and second electron affinity HEQ will be positive and electron affinity will be negative, and this is true for all. Second electron affinity will be negative for all the elements, always true. Because the when we are giving, we have given one electron already and we are adding one more electron, or we are giving one more electron, that that atom cannot accommodate second electron. Because of that we have to give some energy also, so it will take or it will add one more electron in its valence shell. That's why this is always negative. Now we will see the factors affecting electron affinity. Factors affecting electron affinity. First one, Z effective. Z effective we know is the responsible for the attraction of electron to nucleus. So if the Z effective is more, electron affinity will be more, because it can attract one more electron easily. So electron affinity is directly proportional to Z effective. Second, size. As the size will increase, the nucleus to valence shell distance will be more, so the attraction will be less and electron affinity will be less. So electron affinity is inversely proportional to size. Electronic configuration, third factor. Configuration. Half filled and fully filled, for such configuration electron affinity is less because they are more stable than partially filled. Compared to the partially filled, half filled, fully filled is more stable, so it will release less energy. Half filled and fully filled, for such configuration electron affinity is less. In a period, when we talk about in a period, Z effective in period increases. We know left to right it increases, size decreases. So if the size is decreasing, Z effective is increasing, the electron affinity will be increasing, because electron affinity is directly proportional to Z effective. In a group, Z effective is constant, or you can say decreases. Actually it is constant. If you compare the numbers, it's constant, but the size increases because the number of orbits is increasing, so the size will increase and electron affinity will decrease. So down to the group, electron affinity decreases. For this comparison, period and group, we'll see one example. In period, in first period when you see hydrogen is having more electron affinity than helium. Why? Because the left to right Z effective is increasing, but electron affinity will increase. This concept is not applicable here in a period. Half filled, fully filled. Half filled is less stable compared to the fully filled. After taking one more electron, hydrogen's S subshell will be fully filled. So that will be more stable compared to the half filled. That's why hydrogen will show the more electron affinity compared to the helium, and helium is already stable because of the fully filled S subshell. For second period, in a second period, inert gas will have the least. Neon is the second period's inert gas. Then fully filled beryllium, then half filled nitrogen, and then lithium. Lithium is the left element in period and boron is the right element. Still boron will have the less electron affinity compared to the lithium, because after taking one more electron, lithium's S subshell is getting fully filled. That's why lithium will show more electron affinity compared to the boron. Then carbon, oxygen and fluorine. In third period element, here is one important point. Third period elements have more electron affinity than second period elements. Electron affinity of third period elements is more than electron affinity of second period element. Because the third period elements have the last orbit size is big and the second period elements size is small. So when we are giving one electron, the room is less, it will not release the energy as more third period element is releasing. Now for group 13, 14, 15, 16 and 17 P block, we'll see group 13, 14, 15, 16 and 17 we'll see. Here aluminium, because that is a third period element, will have the more electron affinity than gallium, then indium and then boron. For 14th group, silicon, carbon, germanium, Sn and lead. This will be the order for the 14th group. This is for the 13th group. This is 15th, 16th and this is 17th. For 15th, order will be third period element is phosphorus. So first phosphorus will have more electron affinity than nitrogen, then arsenic, first phosphorus, then nitrogen, then arsenic, then Sb, and then bismuth. So for the 16th, sulfur will have the highest, then selenium, then tellurium, and then last oxygen. For 17th, chlorine will have the highest, then fluorine, then bromine, and the last iodine. This will be the order for the period electron affinity for p block elements. Now electron negativity. Electron negativity. This is different than electron affinity. This is a property to attract a shared pair of electron. Okay, property to attract shared pair of electron. It is not a property of an isolated atom like ionization energy and electron affinity. There we were comparing only one atom. We were seeing the property of only one element, but here we are comparing at least two elements. It is a property of bonded molecule. Electron negativity is a property to attract shared pair of electron. For example, hydrochloric acid, you see HCl, hydrogen and chlorine. It is bonded with the bond. This is hydrogen and this is chlorine. So here, because the chlorine electron negativity is more, it will have partially negative charge, and hydrogen is less electron negative compared to the chlorine, then it will have partial positive charge. So here chlorine is more electron negative, and hydrogen is less electron negative. And fluorine, we are talking about now fluorine. Fluorine is good at attracting, but it can't accept the electron because of its less size, small size. That's why when you compare fluorine and chlorine, fluorine will electron affinity for the fluorine will be less because of the small size, and that is the second period element also. And electron negativity, if you compare, it is more. But for chlorine, electron affinity is more, but electron negativity is less compared to fluorine. So chlorine Compared, if you compare with the fluorine, can attract the electron less, but it can accommodate one more electron very easily compared to the fluorine. Now factors affecting the electron negativity, you will see. Factors. First one is electron negativity is directly proportional to Z effective, because it can Z effective is responsible for the attraction of electron towards the nucleus. So this is not, there is not much to explain in. Electron negativity is directly inversely proportional to 1 upon size. Inversely proportional to size. As the size will increase, electron negativity will be less. So then a group from top to bottom, electron negativity will be less. Third one is important. Electron negativity is directly proportional to percentage as characteristics. In the chemical bonding, when you see the hybridization sp, in the chemical bonding chapter, you will see the hybridization. So the hybridizations will come sp, sp2, sp3. Here 50% the bond is S and 50% P characteristics. Here 33% S characteristics, 50% S characteristics, 33% S characteristics, and here 25% S characteristics. So where the S characteristics is more, electron negativity will be more. Now in period, we know the Z effective is left to right more, size is decreasing, so the electron negativity will increase. In a group, Z effective is same, but the size is increasing, so the electron negativity will be less. This is very easy. Now in a Pauling scale, there is a scale for the electron negativity, that is Pauling scale. In Pauling scale, when we calculate for some elements like hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, and chlorine, bromine, and iodine. In Pauling scale, it is coming, the electron negativity for hydrogen is 2.1, for carbon 2.5, for nitrogen 3, for oxygen 3.5, fluorine 4, that is highest, and then phosphorus 2.1, 2.5 sulfur, and chlorine 3, bromine 2.8, and iodine 2.5. So same electronegativity elements are carbon, sulfur, and iodine. They have the same electronegativity. Carbon, sulfur, and iodine. For Pauling scale, there is one more formula to calculate the electronegativity. Pauling scale. Formula is electron negativity of A minus electron negativity of B is equal to 0.101 multiply with bond energy of AB minus root of bond energy of AA multiply with the bond energy of BB. This is the formula for the Pauling scale, and here bond energy of AB or AA or BB will be in kilojoule per mole. So here we complete the electron negativity topic also. Whole periodic table we have completed and we have done very clearly. Now in the next video we'll solve the last year problems from NEET, JEE mains and JEE advanced, and I'll bring some videos where we will solve 15 questions batch in each video. Thank you everyone. Revise periodic table because the concepts will be repetitive in questions also. So you have to revise the concept, otherwise you can forget, and if you forget one concept also you can get the wrong answer. Thank you.